Hello students, so in previous class we have studied about solution of homogeneous partial differential equation involving derivatives with respect to one independent variable, whereas in today's class we'll be studying about solution of Lagrange's linear partial differential equation. So before proceeding on to the problem related to Lagrange's linear differential equation, let us know the working procedure of this. Okay, so working procedure for the problem. So under that, step 1, so this is a standard form of a Lagrange's partial differential equation. So given a standard form of a Lagrange's partial differential equation, here P of the form capital P small p, that's PP plus QQ equal to R. Here P, Q and R, capital P, capital Q and capital R are the functions of x, y and z. Okay, capital P, capital Q, capital R are the functions of x, y and z, and the small p and the small q are the partial derivative of z with respect to x and z with respect to y. Okay, they are the partial derivatives. Small p and small q are partial function of z with respect to x and y. Okay, so next the auxiliary equation of this standard form is given by dx by p is equal to dy by q equal to dz by r. So this is known as auxiliary equation. Okay, auxiliary equation is of this form: dx by capital P, dy by capital Q equal to dz by r. Next, the system of equation can be solved as follows. So how do we solve the system of equation? Step 2, we can consider suitable pairs which can be put in the forms like f of x into dx equal to g of y into dy, which means that dx is a function of f of x. Okay, dx is a function of f of x and dy is a function of g of y. In similar way, you can choose another two pair as g of y into d of y is equal to h of z into dz. Similarly, f of x into dx is equal to h of z into dz. Okay, so this is also called as variable separable method. So that by integration we get the relation in x comma y, y comma z and z comma x. Okay, we get on integrating this. Okay, you get a relation in the form of x comma y, y comma z and z comma x. So that is step 2. So we also have a property in ratio and proportion that a1 by b1 equal to a2 by b2 equal to a3 by b3 is equal to k1 into a1 plus k2 into a2 plus k3 into a3 divided by k1 into b1 plus k2 into b2 plus k3 into b3. Okay, so these are called as multipliers. Okay, so with reference to the auxiliary equation, so what is your auxiliary equation? So this is your auxiliary equation. So with this reference to this auxiliary equation, we try to find multipliers. Okay, we need to find the multiplier. So how do you find the multiplier? That is by a trial and error method. Whatever partial differential equation is being given, Lagrange's partial differential equation is being given. Looking at that, you have to apply a trial and error method. You have to find the multipliers. Okay, so here in general the multipliers are given to us k1, k2, k3, k1 dash, k2 dash, k3 dash, such that dx by p equal to dy by q equal to dz by r equal to k1 into dx plus k2 into dy plus k3 into dz divided by k1 into p plus k2 into q plus k3 into r. Okay, so that is equal to k1 dash, k2 dash, k3 dash. We'll explain you will get to know exactly what is all these when we solve the problem. Okay, don't break your head in this procedure right now. Next, step 3 is you have to integrate the new expression we obtained to relation connecting x, y and z. After you relate a suitable pair, okay, you have to integrate the relation connecting to x, y and z. And this final step is, suppose u of xyz is equal to constant c1 and v of xyz is equal to c2 are the two relations obtained, then phi of u comma v gives the general solution of a Lagrange's partial differential equation. So how do we apply these procedure steps in problem? Let us know that. Okay, so let us begin with the first problem here now. So solve x into dou z by dou x plus y into dou z by dou y equal to z. Okay, so now the given equation is in the form of p plus y q equal to z, where capital P is x, where capital Q is y, and capital R is z. Okay, so p, q, r are the functions of x, y, and z, whereas the small p and the small q are the partial differential equation with respect to x and y, z with respect to x and y. Okay. So next one, the auxiliary equation. We have to write the auxiliary equation. So how do you write the auxiliary equation for a Lagrange's partial differential equation? That is dx by capital P. What is capital P here? X. So dx by x equal to dy by q. What is capital Q here? Y. So dy by y equal to dz by capital R. What is capital R? Compare these two. Alright. Capital R is equal to z. So dz by z. Alright. In the next step, what we have to do is, we have to consider any two pairs. So what will I do is, I'll consider the first two pair. Okay. So consider dx by x is equal to dy by y. Okay. Which on integration will give us. So what will this give on integration? What is the integration of 1 by x with respect to x? Integration of 1 by x is log x. Integration of 1 by y is log y, plus an integral constant log c1. You can choose your constant as anything. You can choose it as log k, you can choose it as log c2, anything you can choose. But make sure that whenever you are integrating, you will always have an integral constant. So I am choosing my integral constant to be log c1. So next you have to apply the property of logarithm. Take this log y to the LHS, so that will be minus log y. So what is log x minus log y? We know that from one of the property of logarithm, log m minus log n is equal to log m divided by n, right? From one of the property of logarithm, we know that log m minus log n is equal to log of m by n. So what is log x minus log y equal to? Log x minus log y is equal to log of x by y. Okay. So that is equal to log c1. So I'll apply anti-log on both the sides. Log and log will get cancelled along with the anti-log when you apply the anti-log on both the sides. So x by y is equal to c1. Okay. So next I'll consider another two pair. Which are the other two pair here now? So first I have considered dx by x is equal to dy by dy by y, right? This is my first pair. So next I'll consider these two pairs, that is dy by y is equal to dz by z. So let us see what will happen when we compare the next pair now. Okay, so consider dy by y equal to dz by z. Okay, so what you will get when you have chosen dx by x is equal to, when you have chosen dx by x is equal to dy by y, what did you get your answer as? X by y is equal to c1. So can you guess what will you get your answer as? Dy by y? Sorry, dy by y equal to dz by z will give you y by z is equal to c2. Similarly, if you choose x and z, then x by z is equal to c3 will be your another term. Okay, so we'll consider two relation because we just need phi of u comma v, where u is equal to x by y equal to c1 and v is equal to y by z equal to c2. Okay, so that is your solution of a partial differential Lagrange's PDE. Okay, so therefore when you consider dy by y equal to dz by z, you get similarly y by z equal to c2. Therefore the general solution of PDE is given by phi of u is x by y now, comma v is y comma z equal to 0. So this is my general solution. Next, let us know a note. Solution can also be phi of y comma z phi of y by z comma z by x equal to 0 and phi of z by x comma x by y equal to 0. Anything it can be, but you should have a two pairs. Okay, two pairs you need to equate to find the solution. Alright. So you can choose anything. If you find that this also it's right, if you find this also it's right. So we'll move on to the next problem now. P into cot x plus q into cot y is equal to cot z. Okay. So what is your capital P here now? P is small p only. So capital P is the cot x, capital Q is cot y, and capital R is cot z. So write its auxiliary equation. Dx by cot x equal to dy by cot y equal to dz by cot z. This is not capital P, this is small p and a small q. So what will be capital P when you compare it with the general form? Capital P is cot x and in the place of capital Q you have cot Y, in the place of capital R you have cot Z. So write its auxiliary equation, then compare the first and the second term. So what do you get? First of all, let me denote this as equation 1. So next, taking the first and second term we have, so let me take the first and the second term. Before that, what is 1 by tan? To integrate this as it is, you can integrate it, but it's not that easier. So what we'll do is, 1 by cot x is also equal to what? 1 by cot x means that is equal to tan x, right? So just write the reciprocal of the cot x and the cot y. Okay, consider first and second term first, and then write the reciprocal of cot x and cot y. So reciprocal of 1 by cot x is tan x. So tan x into dx equal to reciprocal of 1 by cot y is tan y. So tan y into dy. Okay. So which on integration? What is the integration of tan x? Integration of tan x is log of secant x. Similarly, what is integration of tan y? Integration of tan y is log of secant y. So when you are integrating it, you will have an integral constant. Integration of tan x is log of secant x plus integration of tan y is log of secant y plus one integral constant, that is log of c1. So I'll bring this log of secant y to the LHS. So you will get log of secant x minus log of secant y. Apply the property of logarithm, that is log of m minus log n. So log m minus log n is log of n by n. Now apply the property of apply anti-log on both the sides. So you get secant x by secant y is equal to c1. Okay, secant x by secant y is equal to c1. So similarly, if I consider the second and third term, so what is the second term? dy by secant y is equal to dz by secant z. Okay, so that is my second and third term. So similarly, when you compare, you need not do that. You can just write similarly. You get secant y by secant z is equal to c2. If you want, you can work out in a similar way how I have found this. In a similar way, you can find the next one also. Therefore, the general solution of a PD is given by phi of secant x by secant y, comma secant y by secant z. So it can be anything. It can be secant x by secant z, secant z by secant x also. No problem. Alright, you can choose the other two set also, as I have mentioned in the note. So let us move on to the next problem now. Solve y square zp is equal to x square zq plus y. So what will I do here is, I'll bring these two, I'll multiply x square to each term inside the bracket. So y square zp is equal to x square into zp is x square zp, x square into y is x square y, and bring the second term to the LHS and keep x square y as it is and compare it with the general standard form. So when you compare this with the standard form, so this is of the form, what is capital P here? Y square z is capital P, so capital P into small p, minus x square z is capital Q, so capital Q into small q equal to capital R. So capital R is equal to x square y. So after writing it the general form, I am representing it in a general standard form, not a general form, standard form, we have to write its auxiliary equation in the form of dx by y square z dx by p is equal to dy by capital Q equal to dz by R. Okay. So now let me consider the first and the second term. So when I consider the first and second term, what do you get? Okay, I'll denote this as equation 1. So what will I get when I consider the first and second term? I've explained it separately here. See, you have an equal sign, right? So in the denominator, z will get cancelled, right? Z will get cancelled, and you have to apply the method of a variable separable. You know what is variable separable method. See, you have dx, along with dx you have y square, right? And along with the dy you have x square. But along with the dy, it should be a function of y only. And along with the x, it should be a function of x only. Only then you can integrate. If not, you can't integrate it further. Okay. So to integrate this, you have to have a function of x along with the dx and function of y along with the dy. Similarly, function of z along with the dz. Okay. So what will we do is, first of all, let us consider the first and the second term. First and second term. So now y will get cancelled on both the sides. I have shown it here now. You have to cross multiply. So when you cross multiply, minus x square into z will get multiplied with the dx and y square into z will get multiplied with the dy. Okay, so you have, along with the dx you have a function of x and along with the dy you have a function of y. Then you can integrate it. So before integrating it, take minus x square into the other side. That will be plus x square dx. It's not necessary, no, yeah, you have to take it because you have to write it in the form of u comma v. We need to find what is that u, right? So I'll take minus x square dx to the other side. So you get y square dy plus x square dx equal to 0. That is what it's been shown here. Okay. Next what? Dx is a function of x and dy is a function of y. So next step is to integrate. So integration of x square with respect to x is x cube by 3. Integration of y square with respect to y is y cube by 3 equal to c1. So take a LCM, 3 as LCM. So x cube plus y cube is equal to 3c1. Okay. Next we have to consider the last two terms in equation 1. So what we have when you consider the last two terms in equation 1, when you cross multiply, see what is the last term in the equation 1 here now? It is dy by minus x square z is equal to dz by x square y, right? These are the last two terms. So you have equal sign. I'll cancel x square on both the side. Cross multiply. This y will get multiplied with the dy. The z will get multiplied with the dz. That is what I have written here. That is what I have written here. Then take minus z to the other side. It's minus z, right? Yeah. Take it to the other side. So that will be plus z. Okay. So plus z. Then we have to integrate it. So what do you get when you integrate? Integration of y with respect to dy is y square by 2. Integration of z with respect to z is z square by 2 equal to c2. Take 2 as LCM. So when you take 2 as LCM, you get y square plus z square equal to 2c2. Therefore, the general solution of a partial differential equation is given by phi of x cube plus y cube comma y square plus z square equal to 0. Next, we'll move on to the next problem. Y minus z into p plus z minus x into q equal to x minus y. So, what is capital P? Capital P is y minus z, capital Q is z minus x, and capital R is x minus y. Right? It's auxiliary equation. Therefore, the auxiliary equations are dx divided by y minus z equal to dy divided by z minus x equal to dz divided by x minus y. Next, we have to compare the first and the second term. But what we can do here is, even though you compare the first and second term, you have y minus z and z minus x in the denominator, right? So according to step 2, I have told you use the multiplier, right? So what is that method? So when you use a multiplier as 1, 1, 1, each ratio will be equal to dx plus dy plus dz divided by y minus z plus z minus x plus x minus y. So what will I do is, to simplify this further, I will use the multipliers. Please go through the step procedure what I have explained in the beginning. So using the multipliers, so what are the multipliers here? You have to apply a trial and error method. Like, what term if I multiply, I get the denominator equal to 0. You have y minus z minus x and x minus z, right? So if I use the multipliers 1, 1, 1, so what you will get? Dx plus dy, 1 into dx plus 1 into dy plus 1 into dz divided by 1 into y minus z is y minus z plus 1 into z minus x is z minus x plus 1 into x minus y is x minus y. You get your denominator in this way, right? So what gets cancelled? Y minus y minus z plus z minus x plus x will get cancelled. So you have to apply trial and error method, and you have to see to that what multiplier if you apply, you will get denominator equal to 0. It is not necessary that always you have to apply 1, 1, 1. Sometimes you may have to apply x, y, z. Sometimes you may have to apply 1 by x, 1 by y, 1 by z. Sometimes you may have to apply x square, y square, z square, x cube, y cube, z cube, and so on. So looking at the denominator of equation 1, you have to guess what multipliers we need to apply. Okay, so I have applied the multipliers 1 here. So I get the denominator equal to 0. So take this 0 to the other side, equate this with, so you get dx plus dy plus dz equal to 0. Okay, take this 0 to the other side. So dx plus dy plus dz equal to 0, which on integration gives you. What is the integration of 1 with respect to x is x, integration of y with respect to 1 with respect to y is y, and integration of 1 with respect to z is equal to z equal to a integral constant is 1. Okay, so for the next one also, we can't compare, so we have to use a multiplier. Okay, so again what will I do is, I'll use a multiplier x, y and z. So whatever multiplier you use, you make sure that your denominator will be equal to 0. So our next multiplier what I am going to apply is x, y and z. Okay, so when you apply the multiplier, each ratio in equation 1 will be equal to x into dx, okay, plus y into dy plus z into dz divided by x into y minus z. So multiply x to each term inside the bracket. So x into y is xy, x into z is xz. So similarly multiply the second term with the y. Okay, z minus x you have. So multiply each term of z with the x, z minus x with y. So y into z is yz minus y into x is xy. Next multiply z minus y, x minus y with the z. So z into x is xz minus z into y is zy. Okay, cancel all the terms here. Denominator will be equal to 0. Take the 0 to the other side. So that will be equal to x dx plus y dy plus dz. Z dz equal to 0, which on integration of x with respect to x is x square by 2 plus integration of y with respect to y is y square by 2 plus integration of z with respect to y is z square by 2 equal to c2. Take 2 as the LCM, take 2 to the RHS, so you get x square plus y square plus z square equal to 2c2. So your from the first term you got x plus y plus z equal to c1, and from the second multiplier, whatever you have applied, you have got x square plus y square plus z square equal to 2c2. Therefore, the general solution is phi of x plus y plus z comma x square plus y square plus z square equal to 0. Now we'll move on to the next problem. Y square plus z square into p plus x into yq minus z equal to 0. Okay, so what you have in the place of capital P? In the place of capital P, you have y square plus z square. In the place of capital Q, you have to multiply here. X into yq is xyq. So in the place of capital Q, you have xy plus x into minus z is minus xz. So take minus x to the xz to the other side. That will be plus xz. So in the place of r, you have plus xz. Okay. So next we'll write it's the auxiliary equation. So dx divided by y square plus z square, dy divided by xy equal to dz divided by xz. Comparing the first two terms is difficult, so we'll use the multipliers only to when we consider the first and the second term. We can consider the second and the third term. It is very easy to simplify, right? When you consider the second and third term, what gets cancelled here in the denominator? X will get cancelled, and along with the dy you have y, along with the dz you have z. So directly integrate it and find what is the final answer. So let me consider this as the equation 1. So taking the second and third term, we have dy by y equal to dz by dz. So dz by z. So on integrating, integration of 1 by y with respect to y is log y. Integration of 1 by z with respect to z is log z plus the integral constant to log c1. So bring this log z to the other side. So you get log y minus log z. So log of n minus log of n is log of m by n. So log of y minus log of z is log of y by z equal to log c1. Apply anti-log on both the sides. You get y by z is equal to c1. Now, let me consider my first and the second term. Okay. So let me go back to my equation 1 now. What do you have here? Dx by y square plus z square equal to dy by xy, right? So I'll choose my first, you have xy here, okay. So I'll choose my first multiplier to be x, okay. I'll multiply this entire term with the x, and then I'll multiply this entire term with the y, and I'll multiply this entire term with the z, because when you multiply this entire term with the x here, you get x into y square plus x into z square. When you multiply this term with the y, you get x into y square. When you multiply this term with z, you get x into z square. When I find the ratio of it, none of the terms will get cancelled. So what will I do is, I'll consider this as a plus x, and I'll consider the other two terms as minus y and minus z. So let me use the multipliers as x comma minus y comma minus z. So each ratio in the equation 1 is equal to, so multiply first term with x, so x into dx minus y into dy, okay, x into dx minus y into dy minus z into dz, okay, divided by x into y square plus z square is xy square plus xz square, multiply second term with minus y, so x into y is minus xy square, multiply the third term with the z, so x into z is xz square. So all the terms will get cancelled here. plus x square minus x square plus xz square minus xz square will get cancelled and you get denominator equal to 0. So this implies x dx minus y dy minus z dz equal to 0. So your dx is a function of x, dy is a function of y, dz is a function of z. So we can integrate this. So on integration of x with respect to x is x square by 2. Integration of minus y with respect to y is minus y square by 2. Integration of z with respect to z is minus z square by 2 equal to constant C2. So take an LCM as 2. Take that 2 to the LHS. So you get x square minus y square minus z square equal to 2C2. Therefore the general solution is phi of y by z, that is by comparing the second and the third term. By comparing the first and the second term, you get x square minus y square minus z square equal to 0. So this is my general solution. Next we'll move on to the next problem now. X into y square minus z square plus y into z square minus x square into q plus z into x square minus y square. So what do you have in the place of capital P? In the place of capital P you have x into y square minus z square. So dx by capital P equal to dy by. In the place of capital Q you have y into z square minus x square, and in the place of capital R you have z into x square minus y square. So what can we do here? When you multiply this x inside the bracket, what do you get? X into y square is xy square, x into z square is xz square. Here you are multiplying y inside the bracket, so that will be x square y, xz square y, right? I don't think so we can cancel any of the terms if we keep this xyz as it is. If we take off this xyz from this, okay, what will get cancelled? Plus y square minus z square plus z square minus x square plus x square will get cancelled, right? So what we'll do is we have to eliminate this x, y and z from this so that we can make the denominator equal to 0. So what will I do is I'll use the multiplier 1 by x, 1 by y, 1 by z. Okay. So each ratio is equal to, so this will be 1 by x into dx, numerator 1 by x into dx plus 1 by y into dy plus 1 by z into dz. That is what you get in the numerator. What about in the denominator? X divided by x, it gets cancelled, so you get y square minus z square plus y divided by y is 1. So plus z square minus x square, that's what I have written here. Next plus z divided by z and z will get cancelled, so plus x square minus y square. So all the terms in the denominator will get cancelled, so that will equate to 0. Okay. So next equate the numerator to 0. So that implies 1 by x into dx plus 1 by y into dy plus 1 by z into dz equal to 0. So we'll integrate this. On integrating this, integration of 1 by x is log x, 1 by y is log y, 1 by z is log z equal to integral constant log c1. So what is log m plus log n plus log p? Log of m plus n plus p is log of mnp. So similarly, log x plus log y plus log z is log of x, y, z equal to log c1. Apply antilog on both the sides, so you get x, y, z is equal to c1. That is my final answer. Okay. So that is not done. We have to use another two multipliers. So what will we do here is, we'll use the multiplier x, y and z. Okay, in equation 1, I'll use my next multiplier as x, y and z. So when I use the x, y, z as my multiplier, what do I get? X into dx plus y into dy plus z into dz. I guess for the first, when I'm explaining the first multiplier also, I have told you we have to use the multiplier x, y, z. But in a confusion, I guess I didn't multiply y and z. I just multiplied x there. Okay. So if you use the multiplier x, y, z in equation 1 also, so you get x into dx plus y into dy plus z into dx. Similarly to each term, okay, to y square minus z square. Sorry, what do you have in the denominator? You have xy square minus xz square, right? So to that you have to multiply x. So you get x into x as x square y square minus x into x as x square z square. Similarly, what you have your second term as yz square minus yx square. So to the second term also you have to multiply y. So you get y square z square minus y square x square. To the third term you have to multiply z. So z square x square minus z square y square. So all the term in the denominator will get cancelled and your denominator will be 0. Therefore x dx plus y dy plus z dz equal to 0. So on integrating this, you get x square by 2 plus y square by 2 plus z square by 2 equal to c2. Take 2 as a LCM, so you get x square plus y square plus z square equal to 2c2. So that is your final answer. Therefore, your general solution is phi of xyz comma x square plus y square plus z square equal to 0. Next, we'll move on to the next problem now. It's quite similar to the previous one. Okay, we'll directly write its auxiliary equation. Dx by capital P is x into y square plus z. Dy is y into x square plus z minus y into x square plus z. And the r is dz by z into x square minus y square. So first what we can apply, we'll use, it is similar to the previous problem. So first of all, we have to use the multiplier as 1 by x minus 1 by y, 1 by z. Okay. So we have to use those three as a multiplier. We will not use minus, we will use plus only. We will see what will happen. 1 by x, 1 by y, 1 by z. And for the next one, we will use x, y, and I don't think so we can use z as a multiplier for the next one, because you have z into x square minus y square here, right? So we'll think of it. So first of all, let us use the multiplier 1 by x, 1 by y, 1 by z. Okay. So you will have 1 by x into dx plus 1 by y into dy plus 1 by z into dz. When you divide by 1 by x in the denominator, x and x will get cancelled. You will have y square plus z. Similarly, when you divide with 1 by y, y and y will get cancelled. You will have minus x square minus z. Similarly, when you divide the last term with z, you will have plus x square minus y square. All the terms in the denominator will get cancelled, and that will be equal to 0. So therefore, it is similar to the previous problem. So you get the log of log x plus log y plus log z equal to c1. So log of log x plus log y plus log z is log of xyz equal to log c1. Apply anti-log on both the sides, you get xyz equal to c1. It is similar to the previous problem. Now, what multiplier if we apply next to the denominator will get cancelled? If I consider x as the first term, x into y square is xy square, x into z is xz. Okay. Next, if I consider my multiplier as y, x into y is, you already have minus y here, right? So if I choose my multiplier as y, so once again, if you choose your multiplier as x, after multiplying this, you get x square y square plus x square z, right? When you choose your multiplier as y here, you will get x square minus y square, so minus x square y square minus the z square minus the z y square. So you have minus z y square minus zx square here. So for the third term, I'll use the multiplier 1. I'll use the first one as x only. See, you have x, when you use a multiplier x for the first one, you will have x square into z. What you have here, x square into z. Okay, how can you cancel x square into x square z with the last term here when the last term is negative, or if the first term is positive, right? Either you have to choose this as a minus x, but if you choose minus x, then x square y square will not get cancelled with the second term of dy. So what we have to choose the multiplier as, we have to choose the first term as x, second term as y, and third term as minus 1. Okay, each ratio as we have to take multiplier x comma y comma minus 1. So each ratio in equation 1 will be x into dx plus y into dy minus dz divided by x square y square plus x square z minus x square y square minus y square z minus x square z plus y square z. For the third one, I have chosen the multiplier as minus 1. For the second one, I have chosen a multiplier as y. For the first one, I have chosen a multiplier as x. So you see to the denominator, in the same way you have to choose a multiplier. It is not easy, student. You have to make a trial and error method. Whatever multipliers I have used so far, you have to apply all those multipliers, apply the trial and error method, and see to it that the denominator will be 0. So you get denominator 0 with these multipliers now. So you get therefore x dx plus y dy minus dz equal to 0. So on integrating this, you get x square by 2 plus y square by 2 minus z equal to c2. Or x square plus y square minus 2z equal to 2c2. Therefore, the general solution of a partial differential equation is phi of xyz comma x square plus y square minus 2z equal to 0. I hope you have understood. If not, please go through all the multipliers. Okay. So we'll move on to the next problem now. X into z dou z by dou x plus y z dou z by dou y equal to x into y. So what is P here? Capital P is xz, capital Q is yz, and capital R is xy. So I have written an auxiliary equation here. I can directly compare the first and the second one. So when you compare the first and second term here z will get cancelled. When you compare the second and what we can compare? Second and third term we can't compare. Can we? No, we can't compare the second and third term. So let's see what we can do with the second and third term. Obviously, we have to use a multiplier. So first of all, what we'll do is first and second term, it's extremely easy. So we'll compare the first and the second term. So when we compare the first and second term, you get dx by x is equal to dy by y. Z will get cancelled since you have an equal sign. So z in the denominator will get cancelled. So directly integrate this. So on integration, you get log x is equal to log y plus log c1. Bring log x to the other side, so that will be log x minus log y. So log x minus log y is log of x by y is equal to log c1. Apply anti-log on both the sides, so you get x by y is equal to c1. Now for the second term, we have to apply what you have here second term as dy by y into dz equal to dz. Along with the dz, you don't have a function of z. Instead, you have a x and y. But I want function of z here, so I can't. Can I compare the first and the last one? No, I can't do that. So obviously I have to use a multiplier. So what multipliers can I use here? Next, by using the multipliers y comma x comma minus 2z. This is not easy to remember, students. You have to just apply the trial and error method and you have to check what multipliers if we use in the denominator will be equal to 0. So the multipliers I have used here is y, x and minus 2z, because when I multiply, I already have xz as my first term, right? We'll go back to our equation 1. So you have xz here, right? So when you add all the three equations, what you get? Xz plus yz plus xy. So what is missing here? Y is missing, right? So what will I do here is I'll multiply this with the y. So when you multiply this with y, you will get xyz. What is missing here? I'll multiply this with the yz. So when I multiply this with the, I'll multiply this with the x. So when you multiply this with the x, what you get? xyz. So when you add the first and the second term, what you get? xyz plus xyz is 2xyz. So when you add the first and the second term, by multiplying the first term with the x and second term with the y, you get xyz plus xyz, which is equal to 2xyz. So already you have 2xyz when you add the first and the second term. So what you need when you multiply the third term and subtract it, you have to get equal to 0, right? So 2xz minus 2xz is equal to 0, which means that I have to consider my third multiplier as minus 2z. So when you multiply your third term with the minus 2z, minus plus 2xyz minus 2xyz will be equal to 0. Okay. So first term I have multiplied with the x, you get xyz. Next term I have multiplied with, first term I multiplied with y and I got xyz. Next term I multiplied with the x, I got xyz. So the third term I have to use a multiplier as minus 2z. So minus 2z into xy is minus 2xyz. So the denominator will be equal to 0. See here you have y dy plus x dy, right? This is dy, students, not dx here. You have y dy plus x dy, right? Can I write it as the derivative of x into y? Because when you differentiate this, what do you get? What is the differentiation of x into y? It is x into dx, y into dx plus x into dx, right? So y into dx plus x into dy can also be written as d of xy, okay, d of xy. Also you have minus 2 into dz. Can I write minus 2 into dz as a derived differentiation of z square? Because what is the derivative of z square? Derivative of z square is 2z into dz. So 2z into dz can also be written as derivative of z square. Now I'll integrate this. So how can you cancel this differentiation? When you integrate this with respect to xy, differentiation and integration will get cancelled. So you get xy minus. Similarly, you have to integrate this with respect to x here. So differentiation and integration will get cancelled and you get xy minus z square equal to c2. Since you are integrating, you should have an integral constant. So xy minus z square equal to c2 is your final answer. So write it the general solution. So this will be your general solution. Now we'll move on to the next problem. Solve x square into y minus z into p plus y square into z minus x into q equal to z square into x minus y. So what is capital P? Capital P is x square into y minus z. Capital Q is y square into z minus x and capital R is z square into x minus y. Right? It's the auxiliary equation. Dx divided by capital Y equal to dy divided by capital Q equal to dz divided by capital R. So we can't equate any of the terms here. So obviously we have to use the multiplier. See, one of the problem we had a multiplier, we had in denominator x, y and z. What multipliers did we use there? We used a multiplier 1 by x, 1 by y, 1 by z, right? So what multipliers we will use here is, you have x square, y square, z square. So if I cancel this x square, y square, z square, y minus z plus z minus x plus x minus z, x minus y will sum up to, will give you equal to 0. So what will I do is, I'll use my multipliers as 1 by x square, 1 by y square, 1 by z square. Each ratio will be equal to 1 by x square into dx plus 1 by y square into dy plus 1 by z square into dz. Divided by, we have to divide each term in the denominator also. So x square by x square is 1. So what will remain here? Y minus z. Y square by y square is 1. What will remain here? Z minus x. Similarly, z square by z square is 1. Okay, you're multiplying with these multipliers here. X square into 1 by x square means 1 into y by z, so y by z. Y square into 1 by y square means 1 into z minus x is z minus x. Next, z square into 1 minus z square is 1 into x minus y, so this is x minus y. All the terms will get cancelled, your denominator will be 0, so therefore you get 1 by x square dx plus 1 by y square dy plus 1 by z square dz equal to 0. So on integration of 1 by x is log x, but integration of 1 by x square is minus 1 by x. Similarly, integration of 1 by y square is minus 1 by y, and integration of 1 by z square is minus 1 by z. Take all the terms with LHS, so you get RHS, so you get 1 by x plus 1 by y plus 1 by z equal to minus C1. So let me consider, this is however constant, so let me consider minus C2 to be equal to K1. Okay, so that is also a constant. So what am I supposed to do next? Next I have to choose another multiplier, right? So I have to cancel the denominator. So what multipliers can I choose? I'll choose my multiplier to be 1 by x, 1 by y, 1 by z. So let me check whether my denominator will be 0. So 1 by x into dx plus 1 by y into dy plus 1 by z into dz. When you multiply x square with 1 by x in the numerator and denominator will get cancelled. 1x will remain in the numerator. So you get x into y minus z plus y into z minus x plus z into x minus y. You are multiplying even denominator with these multipliers. So 1x will get cancelled, 1x will remain in the numerator, 1y will get cancelled in the numerator, 1z will get cancelled in the numerator. Multiply this x to each term inside the bracket and add all the terms. So all the terms will get cancelled. So you get 1 by x square plus 1 by y, 1 by x dx plus 1 by y dy plus 1 by z dz equal to 0. So this is log x plus log y plus log z equal to log c1. So that is log of x, y, z equal to log k2 they have used, no problem. You can use anything as your constant, no problem at all. So x, y, z equal to 0. Therefore, the general solution of partial differential equation is given by phi of 1 by x plus phi 1 by y plus 1 by z, x, y, z equal to 0. Next, we'll move on to the next problem now. X square into dou z by dou x minus y square into dou z by dou y equal to x minus y into z. Okay. So this is my capital P, minus y square is capital Q, and x minus y into z is capital Q. Therefore, the auxiliary equations are, this is how you write its auxiliary equation. Now I can compare the first and the second term easily, because along with x you have x square, along with dy you have y square. So taking the first and the second term, what do you get? Integration of 1 by x square is minus 1 by x, and integration of minus 1 by y square is 1 by y plus a constant c1. Bring minus 1 by x to the LHS and take c1 to the RHS. So you get 1 by y plus 1 by x is equal to minus c1. Okay, so minus c1 you can also denote it as a k1. Okay, so next what we'll do is, we have to take the last two term in equation 2. So we have after integration. So what you get when you take the last two terms? When you take the last two terms, sorry, this is the wrong one. Once again, we'll redo this problem. So dx by x square minus equal to dy by minus y square equal to dz by x minus y. So we have found the first one. Okay. So we'll consider the second one. So what we have the second one as, what do you have here as the second term here? Dx by x square equal to dy by minus y square equal to dz by x minus y into z. Okay. So according to your procedure, we also have from equation 1 dx plus dy divided by x square minus y square equal to dz by x minus y into z. From equation 1, I'll club the first and second term together and I'll write it as dx plus dy divided by x square minus y square equal to dz by x minus y into z. Okay. So what is x square minus y square equal to? X square minus y square is also equal to x minus y into x plus y. You have to apply the formula a minus b into a plus b. So what is a minus b into a plus b? A minus b into a plus b is a square minus b square, right? So dx plus dy divided by x square minus y square can be written as x minus y into x plus y. So since you have an equal sign, x minus y will get cancelled on both the sides. X plus y will remain here. So you get dx plus dy divided by x plus y is equal to dz by z. Okay. So what is the integration of 1 by x plus y? Before that, you can write dx plus dy as d of x plus y. Okay. You can write it dx plus dy can be written as d of x plus y divided by x plus y. So on integrating this, you get log of x plus y is equal to log z plus log c. To bring log z to the other side, so you get log of x plus y divided by z is equal to log c2, or x plus y divided by z is equal to c2. Therefore, your final partial differential equation is y of 1 by y plus 1 by z, comma x plus y by z equal to 0. This is not so easy as we solve the problem or teach you here, students. If you have any doubt regarding this, you can please drop a text. Alright, so we'll move on to the last problem now. So y square p minus, not the last one, y square p minus xy cube equal to x into z minus 2y. Okay, y square p minus xy cube equal to x into z minus 2y. So what is your capital P here? Your capital P is y square and your capital Q is minus xy and your capital R is x into z minus 2y. So what can we do here? What can we do with this problem now? What changes can we do here? You have y square p minus xy q equal to, so let me consider dx by y square equal to dy by y square. So one y will get cancelled since you have equal sign. One y towards the left hand side as well as towards the right hand side will get cancelled. It's very easy to compare the first and second term. When you cross multiply, this x will get multiplied with the dx and y will get multiplied with the dy, right? And you can directly integrate and you can find the answer. So the integration of x dx will be x square by 2 plus integration of y dy will be y square by 2 equal to c1. Now what can you do with the next term now? We shall consider dy by minus x dy, that is the second and the third term. Okay, dy by minus x into y is equal to dz by x into z minus 2y. Since you have an equal sign, x will get cancelled on both the sides. Okay, dy by minus x into y, so x will get cancelled on both the sides. So what will remain here? Dy by y is equal to dz by z minus 2y. So here dy is a function of y. What about dz? What can we do here? So dy by minus y is equal to dz by z minus 2y. I'll just cross multiply. So when you cross multiply, z minus 2y into dy plus minus y into dz. So bring minus y into dz to the LHS, that will be plus y into dz. Now multiply this dy to each term inside the bracket. So z into dy is z dy. Z into minus 2y is minus 2y dy, y into dz. So I'll club the first and the last term and I'll write it as z into dy plus y into dz. So what is z into dy plus y into dz? Z into dy plus y into dz is also equal to derivative of y into z. Okay, z into dy plus y into dz means it is also equal to derivative of y into z. What is derivative of y into z? Z into dy plus y into, you have to apply the product rule. So when you apply the product rule to d of y z, you get z into dy plus y into dz. Since z is a function of x and y, we can't write 2y into dy as a d of y square. What we'll do is we'll directly integrate this. Okay, so when you integrate this, what do you get? You get yz minus integration of 2y with respect to y is 2 into y square by 2. 2 and 2 will get cancelled. So yz minus 2 equal to, yz minus y square is equal to c2. So this is your required partial differential equation. Right, finally the answer. Next we'll move on to the next problem. X square minus yz into p plus y square minus zx into q equal to z square minus xy. So this is your capital P, this is your capital Q, and this is your capital R. So write its auxiliary equation dx by x square minus yz. Next dy by y square minus zx and dz by z square minus xy. We have to write its auxiliary equation. Next, what we can do is we'll equate equivalently. What we can write this in the form of dx minus dy, dy minus dz, and dz minus dx. Okay, we'll write this in the form of dx minus dy divided by x square minus y square. I'll club these two terms together. See, because you have x square, y square, z square, minus yz, minus zx, minus xy. As it is, if you write multipliers, if you use, you can't solve this problem. So what we'll do is, we will write this in the form of dx minus dy divided by x square minus y square. I'll club together. I'll take the positive term outside. So plus into you have minus here, right? So minus into minus will be plus. The second term will be plus. So I'll take plus z outside. So what will remain inside the bracket? X minus y. What you have to do is write all the denominator terms first. That is x square minus yz minus of y square minus zx. Then multiply that negative terms to each term inside the bracket. So when you multiply negative term to each term inside the bracket, minus into plus y square is minus y square. Minus into minus zx is plus zx. So that is what you get, and that is how I have separated the term. Similarly, dy minus dx is divided by y square minus z square. This term will be positive. So from the second term, I will take plus x outside. So what will remain inside the bracket? Y minus z. Next, dz minus dx. So z square minus x square. This term will be positive. I will take a plus y outside. So what will remain inside the bracket? Z minus x. So what am I supposed to do next now? So next what will I do is, here you see you have x square minus y square, right? So what is x square minus y square? It is x minus y into x plus y. So if you take x minus y as a common term from these two terms, what will remain inside the bracket? X plus y plus z. Similarly, y square minus z square means what? It is also equal to y minus z into y plus z. So if you take y minus z as a common term from the first and the second one, what will remain inside the bracket? Y plus z plus x. Similarly, in the last one, z square minus x square means it is also equal to z minus x into z plus x. So z minus x, if you take common from the first and the second term, what will remain inside the bracket is z plus x plus y. Z minus z plus x into z plus x plus y. So this is what you get. Dx minus dy divided by x minus y into x plus y plus z equal to dy by dz divided by y minus z into x plus y plus z equal to dz by dx divided by z minus x into x plus y plus z. So if you equate the two terms here, x plus y plus z will get cancelled everywhere because you have equal sign, and all the denominator x plus y plus z is common. So everywhere x plus y plus z will get cancelled. And what will remain? Dx minus dy divided by x minus y, dy minus dz divided by y minus z, and dz minus dx divided by z minus x. Now it is easier to compare and to solve the problem. So firstly, let me consider the first and the second term. So dx minus dy can also be written as d of x minus y. Okay, dy minus dx can also be written as d of x minus y. So d of x minus y divided by x minus 1. So what is the differentiation of 1 by x minus 1? So I have compared the first and the second term. Second term also, you have dy minus dz as the denominator. You can also write it as d of y minus z. So on integrating this, what do you get? Integration of 1 by x minus y is log of x minus y. Integration of 1 by y minus z is log of y minus z plus log c2. On integrating this is what you get. Now bring log of y minus z to the LHS. So you get log of x minus y minus log of y minus z is equal to log c2. So log m minus log n is log of x minus y by y minus z. Apply anti-log on both the sides. You get x minus y by y minus z is equal to c1. Similarly, for the next one, you compare the second and the third term. So you get y minus z by z minus x is equal to c2, because what you have, dy minus dz by dz minus dx. Okay, so you get y minus z by z minus x. If you want, you can do the entire procedure, how you have compared the first and the second term, how you have taken d outside and written it as x minus y and y minus z. In a similar way you can do for the second term also, or else you can directly write this. It carries the marks, no problem. You can write it as a general solution. Okay, so it's the general solution is phi of x minus y by y minus z, comma y minus z by z minus x is equal to 0. Next one, x square minus y square minus z square. So this is capital P plus 2xy, this is capital Q, equal to 2xz. So this is capital R. So write its auxiliary equation. Okay, so after writing its auxiliary equation, I'll compare the second and third term, because when you consider the second and third term, you have an equal sign and 2x will get cancelled on both the side, right? 2x will get cancelled and you get dy as a function of y and dz as a function of x. Next, let us think about the first term. What we can do with the first term? Now, we'll compare the second and the third term. So by taking, not comparing, by taking the second and the third term, 2x will get cancelled and you get dy by y is equal to dz by z. On integrating this, you get log y is equal to log z plus log c1. Therefore, y by z is equal to c1. What can we do with the next term is you have x square minus y square minus z square, right? So let me choose my multipliers as x, y and z. So you get x dx plus y dy plus dz divided by x into what you have there, your denominator as x square minus y square minus z square, 2xy and 2xz. So x square minus y square minus z square. I'll multiply these three terms with x. So you get x cube minus xy square minus xz square. Next term I'll multiply with y. So 2xy into y is 2xy square. Third term I'll multiply with z. So 2xz into z is 2xz square. Now x cube I'll keep it as it is. Okay, sorry, x cube I'll keep it as it is. What is 2xy square minus xy square? 2 minus 1 is 1, so you get 1xy square. Similarly, 2xz square minus xz square is 1xz square, so you get plus xz square. So from this I'll take x as a common term. So when you take x as a common term, what will remain inside the bracket? X into x square plus y square plus z square. X into x square plus y square plus z square. So now what will I do is, after choosing the multiplier, I have x into x square plus y square plus z square here. So I'll consider dy by 2xy is equal to x into dx plus y into dy plus z into dz divided by x into x square plus y square plus z square. Now x will get cancelled on both the side. 1x will get cancelled on both the side. I'll cross multiply. Cross multiply as in dy by y will remain as it is. Sorry, you are not supposed to cross multiply because you have x into x square plus y square plus z square in the denominator, right? So after x gets cancelled, you just take this 2 to the numerator. Okay, so you get 2x into dx plus 2y into dy plus 2z into dz. So on integrating this, what do you get? This can also be written as 2x into dx plus 2y into dy plus 2z into dz you have. So on integrating this, what do you get? Integration of dy by y is log y. But what is the integration of this entire term? Integration of this entire term is log of x square plus y square plus z square. Right? Integration of what is 1 by x square? This is a vice versa method. See, what is the differentiation of x square plus y square plus z square? How do you write it as 1 by x square plus y square plus z square? Plus differentiation of x square is 2x into dx plus differentiation of y square is 2y into dy plus differentiation of x z square is 2z into dz, right? So in a similar way, what is the differentiation of integration of 2x dx plus 2y dy plus 2z dz by x square plus y square plus z square? It is equal to log of the denominator. If you have of the form, I hope you know that, if you have in the form of f dash of x divided by f of x, then it is always equal to log of f of x. You have to always remember that. Okay, if you have in the form of f of x in the denominator and differentiation of f of x in the numerator, okay, if you have f of x in the denominator and differentiation of this denominator if it is in the numerator, then it is always equal to log of denominator. Okay, f dash of x by f of x is always equal to log of f of x. Is always equal to log of f of x. So this is also equal to log of x square plus y square plus z square plus an integral constant. Now bring this log of x square plus y square plus z square to the denominator. Apply anti-log on both the sides. So you get y by x square plus y square plus z square equal to c2. So that is your required partial differential equation. Next we'll move on to the last problem now. Mz minus ny is capital P, nx minus Lz is capital Q and mx minus Ly is capital R. So take this capital R to the LHS. So when you take this capital R to the LHS, mx minus ly can also be written as ly minus mx. So that will be a capital R. Right? It's auxiliary equation. Okay. So what I have done here is I have shown that taking mx minus ly. So when you take the negative term first, that will be ly minus mx. So write its auxiliary equation. So what we can do after writing the auxiliary equations here, we can write this as dx minus dy because you have mz minus mx minus lz ly minus mx, right? So I'll write this in the form of dx minus, okay, first of all let me use the multiplier. Okay, I'll use a multiplier as L, M and N because what you have here previous step, you have M, Z minus NL, right? So what if you use a multiplier? M and N you have, what is missing here? L is missing, right? So I'll use a multiplier L. Here you have N and L. So what is missing here? M is missing, right? So I'll use a multiplier M, and for the last term I'll use a multiplier N. Okay. So I'll use a multiplier N, L, M and N. So you get L dx plus N dy plus N dz. Similarly, when you multiply the first term with L, second term with M, third term with N, denominator will be 0, and integrate the numerator, so you get Lx plus My plus Nz equal to C1. Okay, so that is your first answer. What we can do for the next one is, what is missing here? We'll go back. What is missing here? You have y and z, right? What is missing? X is missing. What else you have? You have x and z. Y is missing here. Next, what is missing here? You have x and y. Z is missing here. So we'll use our next multiplier to be x, y and z. Okay, we'll use our next multiplier to be x, y and z. So in equation 1, so you get x into dx plus y into dy plus z into dz divided by, multiply the first term with x, second term with y and third term with the z. So the denominator will be 0, and integrating it you get x square plus y square plus z square equal to 2c2. So this will be your required partial differential equation. I hope you have understood all the problem. Actually using the multipliers it's not so easy because you have to apply a trial and error method. But whatever problems I've solved here, please go through these problems because usually you can use the multipliers, whatever I have applied here, and use the logic like what multipliers you can use looking at the denominator so that the denominator will be equal to 0. Thank you.